All right, so we are going to go back to some more just indefinite integral examples just to continue to work on some U substitution ideas. And I'm going to go back to an example that we did before, and we're going to kind of compare it to some similar looking integrals. So we have done this integral from, just an indefinite integral. We've done this 3 over 4x squared plus 16 before, and I have the picture off to the right. And we did it 2 different ways initially. And I'm going to show you what really would be my favorite way to do this one. So the first way, if you only rely on knowledge of this fact, the integral of 1 over 1 plus x squared is tan inverse of x. And so I have some instructors that never really show those little formulas we have up above, some books that don't highlight those as well. And if you only use your knowledge of that, the first thing you need to say, okay, it kind of looks similar, but the first thing we did is we get a 1 where the 16 is, and so we factored out the 16. And then we brought the whole 3/16 out in front. Then we were close, but it still wasn't just 1 over 1 plus x squared. And so it still required a little u substitution there on that 1/2 x, and we finished it out that way. The other way was to use the formulas that we had up above here. So we had this formula for the integral of 1 over 1 plus a squared plus x squared. And so we had this formula. So one way to use that formula is to say, okay, this looks pretty similar. I have this 1 over 16, that's like my a squared, and I have some kind of an x squared. I can just do a u sub on that. The u can be 2x, and then it matches up perfectly. I'm going to show you what how if I was just told to do this integral, how would I do it? So I probably would have made this choice. So I'll be honest, probably because how I learned, I did learn initially those formulas. So I tend to use those. Not all instructors or books do. So for me, I kind of think about, okay, I do have knowledge that if I can get something into the form of 1 over a squared plus x squared, I know how that will integrate. It's going to be this 1 over a tan inverse of x over a. I know that. Now, the thing we have to be careful of when we use this is the constant part, the a, that's not a problem. Even if it's not a perfect square, you could write it like if it's 10, you could say root 10 squared. The thing we have to be careful of is it can only be, and I've emphasized this really with any of the approaches that we've taken, this can only be a plain old x squared, and it's not, right? So what's keeping me right now from applying that formula directly is this 4. That's what's keeping me from applying the formula directly. So there's 2 ways to deal with that. One is do a u sub, and that's what I did down here the last time we did it. That's important. There will be times you will have to do that. What I'm going to do here isn't always going to be possible. So there will be many times, especially imagine if this was e to the 2x and then you wrote it as e to the x squared. Like there will be times you will have to do a u sub. But in a case with just a constant like this, if this is my problem, I can, since it is just a number, I can factor it out. And so I would have 4 times the quantity of x squared plus 4. Okay, well that now means that I can rewrite this integral. I can bring the 3 out in front. I can bring that 1/4 out in front, so I have a 3/4. So now I'm going to have just my 1 over, and then what's left is that binomial, right? And the binomial is 4. 4 is really, if we want to think of it for purposes of the a squared, 4 is going to be the 2 squared plus, and now I do just have a plain old x squared. That plain old x squared is really the crucial piece, I would say, in being able to apply this formula directly. And so again, the time before when we did it with the formula, we said that we could do a u sub, and certainly that's true. But this is the other way to handle it in the case of a constant like this. So for me, this is definitely how I probably would have approached this. So I would have my 3/4 carried along as a constant multiple, and then if I know this formula, I have my 1/2 and then my tan inverse of x over 2, because 2 again is the a, plus c. And so of course, this is like the third time we've done this one, but we're of course getting the same thing here. So we get 3/8 in this tan inverse of x over 2 plus c. So the real crucial thing really with any of these approaches that have been taken is that in any of them, what was the commonality was really realizing that in order to apply even the most basic, just the antiderivative 1 over 1 plus x squared, it has to be just a plain old x squared. In order to be able to use the formula form, the 1 over a squared plus x squared, kind of that extension of the basic one, you still need a plain old x squared. If you don't have a plain old x squared, you either need to do a u sub, that's kind of the more general way to approach it, like we did at the bottom down here. Do a u sub in order to get it as just a 1 over u squared plus a squared. Or in this case, just dealing with constants, you can factor out that constant. Makes kind of short work of it, but in other situations, you do need this kind of u sub idea. All right, so now what I want us to do is I want us to contrast that integral in any of the three forms that you want to think about having evaluated it. But I want us to think about the difference between kind of the look of that one with the look of, what if I just gave us the integral of 3x over 4x squared plus 16? So these comparisons, the further you go, we have all these different similar looking, often similar looking integrals, and we need to recognize the correct approach. So you want to go through your, okay, first, could I do some quick algebra and get it term by term x's to powers? No way. It's a monomial divided by a binomial. You can't, quote, split it up. So the next thing we look at, and this is kind of your order of thought, can I do a basic u substitution? And in this problem, there's not something inside of an outer power, but there is an entire denominator. And we have seen that many times that is what we pick for our u. And on this one, that is going to be exactly what's going to work. If I let u equal 4x squared plus 16, my du in this case is 8x dx. So what you want to start thinking about as you're doing and setting up all these various u substitutions, mentally, as you're picking your u, be thinking about, okay, when I take that differential, do the variable components match up with what's left? You're picking a u so that when you take the du, the variable components, we hope, match up with what's left. If they do, it's a basic u sub. So u is 4x squared plus 16. Oh, du is 8. Who cares about constants? We can always adjust for those. But I get the x dx, and that's what's left in the original integral. So this is our most basic u sub. But often, after we've learned all these other things, like these, inverse trig functions and all this other stuff that we've done, we start to go back to ones that before we learned anything about those, we would have just handled a little bit, probably more easily, by just identifying the basic u sub. And now sometimes we'll have a tendency to overcomplicate things that are just basic u subs. So as we look at this, we now see, okay, so this is going to tell me I'm going to have my 3 is going to just get carried along in front. I'm also going to bring the 1/8 out in front as well. And then I'm just going to have my 1 over u du. So this one, so again, the 1/8 du, and then this was my 1 over u. All right, excellent. So this becomes my 3/8 natural log of the absolute value of u. And of course, that's just 3/8 natural log of, and in this case, you can actually drop your absolute value bars because 4x squared plus 16 is already going to be positive. Okay, so we can just go with that. All right, now let's do one more kind of variation on this that kind of has a similar look. So suppose we have this time 3x squared over 4x squared plus 16 dx. So this will be a little different than all of the above ones. So first of all, it's not going to be my basic u sub. And let's think about what the main issue would be, right? So if u was equal to the 4x squared plus 16, okay, so I'd have like my 1 over u. But then if my du was then just the 8x dx, yeah, sure, I can divide by 8. But then x dx, and there's two x's up there, right? So that x squared is like an x times an x, and only one of the x dx's would be equal to this 1/8 du. I would still have an extra x, and we have said that is a problem. This doesn't make any mathematical sense. Now, we did have an example in the last video where sometimes we can replace a lingering x in terms of u, but not when the u is as complicated as this. I mean, think about what this would look like. You'd subtract 16, you divide by 4, that would give you x squared, and then you'd have to take, your plus or minus square root of that, and you want to put that in for your x. That's not something that we're going to be able to more easily integrate. So this is what's going to happen as you're doing your u substitutions, is you're going to try things and you're going to fail. And recognizing when they don't work is probably one of the most important things, and not forcing it through. I'd rather have a student stop and say, this doesn't work, I'm stuck, I don't know what to do, but this didn't work, than to just like force it through and carry along an x. That's like, I couldn't get it set up right, and then I think that this incorrect thing is okay. So we've got to recognize when it doesn't work. That didn't work. So you're going to work a lot more in integration in Calc 2, but there's just something that I want to show you here, and that is going to be that oftentimes when you have a degree of the numerator equal to the degree of the denominator, greater than or equal to, you can either do like a long division, or you can kind of add in a fancy zero. So first on this one, maybe if I didn't see anything else, I might be tempted to at least factor out the 4. Like, I tried my u sub, it didn't work. I might start to think almost like part A. I might be tempted to say, well, I mean, what else could I do? Maybe I can factor out a 4, and that's okay. That's just going to make it look a little nicer. So I could certainly rewrite this as like this 3/4 as a constant multiple. That certainly has made it just look a little bit nicer, but it's not going to change the issue that u substitution doesn't work. And it also doesn't change the issue of, let's just also mention, this is not an arctan situation. And the main reason being, look up at your formula up above, or any of the formulas that we have here off to the side. This is not something that is going to match up with in this case, the closest one being the arctan, because of that x squared in the numerator. You're not just adjusting by a constant, or you're not just doing like, oh, I need a little u sub in the denominator. So that big x squared in the numerator is stopping this from being arctan. So what I was starting to say, and this is something just to kind of think about as you move forward into Calc 2 as well, is that, so we'll put a little thought bubble out here. And I don't know that you're going to have a lot of these this semester, but this is something just to keep in your back pocket. When the degree of the numerator is greater than or equal to the degree of the denominator, often there's an algebraic little thing you can do. You can do the division. So you can do in this case it would be long division, right? But I'm just going to say do the division. Or in some cases, like this one, so I'm just going to say, I'll even write that, in some cases, and that's probably what I'm going to show you here, you might be able to, what I often call in class, you're going to add and subtract, and basically this is going to end up equaling basically like adding in what I call a fancy zero. So we're going to add in a fancy zero. This is what I would say in class. I'm trying to come up with a way to write this in words on a video here. But yeah, I might say let's add in a fancy zero. So we're going to add and subtract the same number. And when we do that, it's adding in a fancy zero. So when the degree of the numerator is bigger than or equal to the degree of the denominator, in those situations, you can oftentimes add in a fancy zero. Okay, so let's go ahead and think about both of those approaches here. So if I was to do the division, so suppose I did just that. So let's just kind of think about here for a second. Let's say I actually did the division approach. All right, so doing the division would look like the x squared divided by x squared plus 4. And then you'd say, okay, x squared divided by x squared is 1, or x squared times what gives you x squared? It's 1. And then you'd say, oh, that's x squared plus 4. And then you'd say, oh, I need to then change the signs or do the subtracting. And then you'd say, oh, that's negative 4. And so my remainder in this case is just minus 4 over that divisor of x squared plus 4. Okay, so this is the doing of the division part. Okay, so this is one way that you could choose to go. All right, so that's one thought. Now, what does that mean? We just found out that x squared divided by x squared plus 4, we just found out that that is equal to the quantity 1 minus 4 over x squared plus 4. So when, this will be something that you'll probably get emphasized to you in Calc 2 as you start to develop more integration techniques, but when the degree of the numerator is greater than or equal to the degree of the denominator, oftentimes you can just do that division, and that's going to get it into a different form that you can actually then integrate. What I often do, and I look for on problems like this, and it doesn't always occur, but actually it works out okay here. So sometimes you can add or subtract in the same number, or what I call adding in a fancy zero, and you can get there just a smidge more quickly. So on this very same definite integral, if I was to say, let's think about I'm just going to kind of rewrite it here. In the numerator, if I was to both add 4, and so this is really what's motivating it. I'm trying to get a version of 1 here. So adding 4 would create 1, but I can't just add 4. That would change the value. But if I subtract 4, I've added in a fancy form of 0, so I haven't changed anything in terms of the original. So I have created what really is going to be the same thing by adding in this fancy 0. Because now, if we then think, oh, well, look, I could rewrite that and I could split this up according to saying I could take the x squared plus 4 over itself, and that is what's going to get you to the 1, and then minus the 4 over the x squared plus 4. And of course, that's now this second term. So we have two different ways that we can kind of think about getting there. And so the first one was doing the division. And so this is one way to go. The other one in this particular problem that's kind of cool, right? Just plus 4 minus 4, and I get to break it up. All right, so again, this may be something that you see more in Calc 2, but I'm trying to expose you to a little bit of it now, and you may see it in some of your homework as well. So this was kind of an algebraic tool, an algebraic manipulation that allows us to get this into a form that we can actually integrate. So the 3/4 is carried as a constant multiple, and now the integral of 1, I don't know why I made that a bracket, a parenthesis would be just fine. So the integral of 1 is just going to be 1x minus, and now on this second term, think of this 4 as a constant multiple, but now we know that the integral of the just what we had up above here, I'm going to slide this formula over here. So there it is right here, the second one. So the integral of the 1 over a squared plus x squared is the 1 over a arctan of x over a. We are exactly in that form. So this ends up becoming, so we have our 1 over, and once again, the a in this case, the 4 squared is the, or 2 squared is the 4. And so we have the 1 over a, which I meant to actually just write in as 2 there. So we have the 1 over 2 times the tan inverse of x over 2, and that's from our arctan formula. So we're really looking at, in that case, is we're really looking at realizing that we have with the, I'll just kind of highlight, that's like a 1 over x squared. So if we think about that as just kind of being kind of like times, almost like a little 1 here. So that is where we got this whole result right here. So we're just using that formula for the 1 over a squared plus x squared. So that was part of the reason too why I wanted to start off. I should just scroll down here or scroll up. That's how we did that part A, really, right? So we just did the 1 over 2 squared plus x squared. All right, so we're basically here. So what do we have here? So that's our final answer. So we end up with just exactly, if you want to distribute the 3/4 through, you can. You'd have 3/4 x minus, and then I guess we'd have then a 3/2 tan inverse of x over 2 plus c. All right, so look at those 3 integrals. Take a second for yourself and kind of compare them and notice how all 3 were different, but yet they all looked so similar when we started. So that's one of our key observations that we really want to make here. All right, so that was number 1. So there's so many other things that can come up with our integration here. So number 2, let's take a look at this one. I want to drive home a point I was saying earlier. Suppose we have the integral of 7 sine x over cosine of x times the square root of cosine squared x minus 16 dx. So the first thing, of course, is just make sure that you're always kind of thinking of that cosine squared as really being the cosine of x quantity squared. So make sure you're aware of that. Now, again, what I've been saying, you're going to try things, if I go with the obvious inside idea here, I would probably start, and a lot of you will, you're going to say, let's let u equal what's under that square root. And there's nothing wrong with that. You'll get better at recognizing almost mentally before you even write it out why it's not going to work. So if I take this derivative, it needs chain rule. So 2 cosine and then derivative of cosine by chain rule, so I have a minus sign there. Okay, and this is a problem. While I do have a sine x dx, so I could divide by the negative 2 cosine x, this is a problem because sine x dx, so if I look at kind of what would be happening with this integral, I'd have a square root of u, I'd have a 7, who cares about that? My sine x dx portion in the numerator is being replaced with this du over the negative 1/2. I can bring that out in front. But there's an additional that comes from this du factor. There is an additional cosine x in the denominator that's resulting. Not to mention, there's also a cosine x that's still left over in the original integral. So this is not looking too good. I have a lot of functions of x left over. Could I maybe in this case make a go of going back to that original u? I probably could, because I happen to have kind of lucked into, in this case, I have a cosine squared that's left, and u is cosine squared minus 16. I could maybe replace both of these with a u plus 16, and this is often what happens. Like together, these are cosine squared, and that would be u plus 16. But now I'm at a point that I still can't integrate it. So these are going to be the rabbit holes that you are going to go down. You're going to try a u substitution. You're going to feel really competent and confident because you're going to say, I know what to do with sine x dx, and it gets replaced with this du over negative 2 cosine x. And oh, awesome, cosine that's left and a cosine that's there. That's cosine squared, and I could replace that with a u plus 16. But here's what often will happen. What you get, you can't integrate. Like, I don't know what to do with that. That doesn't look like anything I know how to do. So this is kind of how some of your integration is going to work. You're going to try things. You're going to bring in and incorporate elements of different examples that we've done. And you're going to get mad at me in your head because you're going to be like, well, it worked in the one she did. But this is the nature of integration. It's an art form that takes practice. So we go back to this integral, and that didn't work. The primary inside just didn't really work. It took me down a rabbit hole that I eventually still couldn't integrate. But I do kind of have another inside function here, and it's a cosine. So I have a cosine here that kind of looks like something inside of a function that's being squared. So that's another inside type of function there. In addition, I want you to start to be on the lookout for these binomials that look like some sort of function of x squared minus an a squared. So we're thinking u squareds minus a squareds, or sometimes plus if it's arctan, or sometimes if they're minus. You want to be on the lookout for things that are these binomials in denominators of a squareds plus function squared, or a difference. Because, and I still have this over to the side here, look at these 3 formulas that we have here, that a lot of times you're going to be able to incorporate with a u sub. So what I want you to kind of notice here is, yeah, that cosine is an inside, but even more specifically, this is looking like a u squared minus a squared. So like this is kind of what I want you to be thinking of. And when you see these u squareds minus a squareds, I want you to be thinking, is it possible that I could get this into one of those inverse trig type of formulas? All right, let's continue with the attempt on this u. So my du is going to just be sine. Du is sine x dx. Okay, so we're going to have our, erase this. Oh, sorry, I just minus sign. Minus sign, derivative, cosines, minus sign. All right, let's erase here. All right, now let's look back at what we have. So what do we have? What's left in my du, or in the integral, I do have a sine x dx, and I do have a sine x dx down here. So I like the look of that. So of course dividing, both sides here by this -1. So I get that negative du is equal to sine x dx. So this looks promising. What maybe isn't 100% promising, of course, is still going to be this problem that is in the denominator, that extra cosine x. So this right here is still left over as somewhat of, maybe initially we think of it as a problem, because it certainly would not make sense to say the integral of -7 du over square root of u squared minus 16 times cosine x. Like, this doesn't make any sense, right? So we've said that a lot. So that's nonsensical stuff. But this is like the easiest problem to get rid of because it's just an extra cosine. And guess what? I have that u is equal to cosine of x. So that is going to be another u. So let's see where that takes me. Maybe I do all this and I don't have something that I can even integrate. That happened the first time. So let's see what happens. All right, so I am going to have my 7 just kind of carried along in front. My sine x dx is being replaced with the negative and the du. And that's going to leave me with, I guess, just kind of a 1 here in my numerator. And then over, that's going to be my u times the square root of u squared minus 16. Okay, so I replaced the cosine and the extra cosine. Those both got replaced with u's. And then my negative du was the replacement for the sine x dx. So this one is perfect. This is exactly what we know to be. So I'll even write it here. So here's what we know. We know the integral of 1 over x times the square root, obviously in this case it's u, of x squared minus a squared is equal to 1 over a secant inverse of x over a plus c. And if you don't work out of our Sullivan book, then your secant inverse may have absolute value bars around that x. Our book defines some things early on a little differently. Okay, so this is perfect. I know exactly what to do with this. Of course, the 16 here, I can just think of my 16 as just being that 4 squared. So every place where there's an a, that's really just going to be 4. So this is perfect. So we now have this negative 7, and that's going to get carried along times. Now, we're going to have 1 over, our a in this case is the 4, times our secant inverse, or arcsecant, of x over, and our a again here is 4 plus c. So there it is. We have a negative 7/4 secant inverse, or arcsecant, of x over 4. Oops, I made a mistake. It's not x, it's u. And you'll do that from time to time too, I'm sure. U needs to be replaced with what it was originally, which was cosine of x. So our final answer is negative 7/4 secant inverse quantity of cosine of x over 4. So this was a nice set of examples for us to focus on that involved the comparison, kind of utilizing a little bit more some of these, the formulas that we talked about before, and then also just some side-by-side comparisons in that first set of examples there of things that look similar but were all slightly different approaches.